Do you care about security in your home lab? Are you sick of all those "do you trust this website" warnings all over the place, telling your friends and family to ignore them every time they want to connect to your Plex server? Today we're going to fix that. By taking a little thin client like this and a Yubikey, we're going to make our own certificate authority. This is just like Let's Encrypt, and it works the same way, only we trust it ourselves. We can give out certificates on our own, and anyone that trusts our root key will trust all of our websites. Come along with me on this adventure. So what is a certificate after all? Well, certificates are part of public key cryptography. Essentially, mathematically, if I generate a private key and keep it private, and from that key I generate a public key and give that out to everyone, everyone can verify if something was signed using my private key. So, I'm Applard, I write out a certificate. It says, I am Applard at www.applard.net. Then I sign that with my private key. If you take that certificate, you can validate my signature actually did come from me if you trust my public key. So, I'm a web server. I do what web servers do. I generate my own private key so I can sign TLS transactions. I make a certificate. I send it out to the client. The client checks and says, oh, look at this web server. Should we trust it? And we get that. I guess they don't trust my web server. So why don't they trust my web server? If we look at the certificate in detail over here, it says the common name is terra.panlet.net, and sure enough, that's where we're going. So at least the domain name matches. We're not trying to forge that. So who issued the certificate? Well, Proxmox Cluster Manager CA. So it looks like my web browser doesn't trust Proxmox Cluster Manager CA. And this is what happens for most self-hosted sites and most things in the home lab. We generate our own TLS certificates. We get encryption, but we don't get that validation that everything's truly up and truly correct. So how does a real website look? So this is my own website. This is my certificate. So I have a common name of www.applard.net. That's my domain name. And it says it's issued by R3 Let's Encrypt. So if we look at the chain details, so my certificate was signed by R3, and R3 was signed by ISRG root x1. So what that means is that my server, www.applard.net, got its certificate and then asked someone more important to sign it, and that person was Let's Encrypt. And Let's Encrypt went to someone even more important, and they signed their own certificate, ISRG root x1, and my web browser, Edge, implicitly trusts that ISRG root x1 certificate. So because ISRG root x1 signed a certificate for Let's Encrypt, and Let's Encrypt then used that key to sign my certificate, there's a chain there, a chain of trust. So what we like to do today is establish our own chain of trust for our home lab. We're going to create that top dog, that root certificate. And then we're going to sign an intermediate certificate that we can use to issue more certificates to all of our home lab services. So, like all of these websites out in the public that go to Let's Encrypt to get their public certificates, we can go to our own certificate authority to get our own internal certificates signed and verified by our certificate authority. And this works even if we don't have public internet access, or even if we don't have internet access at all, because it's all self-contained in the home lab. Our certificate authority runs on our own local hardware. It signs certificates, everything's on the up and up, everything's happy. Another advantage of this is we can use really short-lived certificates. So if one of our VMs is compromised, if that private key that's on the VM's drive is leaked out on the internet, it might only be good for 24 hours before a new one gets generated and signed. But if we're going to rely on that for security, how do we make sure our certificate authority stays safe? We use a Yubikey. You've probably heard of these things before. It's called a Yubikey. But these things can be used to store securely private keys, and they can sign certificates using the private key in hardware. So if someone were to hack into my certificate authority, they could sign things using the hardware key, but they couldn't take the key itself and copy it somewhere else. They'd only be able to ask the hardware key to sign things for it. And if I unplug the hardware key, they can't do that anymore. So for someone to have access to my private key, they would actually have to steal the dongle. And even then they wouldn't have the private key itself, they'd just be able to use the private key. So it makes it a lot harder for a hacker to get access to all of our data. Not impossible, but it's an extra layer of security that I like. So in a sense, we're going to generate three levels of hierarchy. We're going to generate our root. We're going to keep the root on the special Rubik's Cube flash drive, and it's going to be encrypted, offline, never going to touch the internet. Then using the root, we're going to generate and sign a certificate for our Yubikey, which is going to stay connected all the time to the certificate authority. And then the certificate authority can use that Yubikey to sign short-lived certificates for individual servers. Hopefully that's a good enough overview of how certificates work for you. Let's get to setting it up. So before we can set up a certificate authority, we need that God tier private key. Let's generate that now. I can't stress this enough. Don't leave your private key around. Your root private key is like, gotta keep it safe. So one way you could keep it safe is by putting it on a flash drive like this and wiping the flash drive before you generate the key, generating the key on the flash drive using a live USB on like a little computer like this, and then rebooting. Then the flash drive is the only place with the root private key. Keep this safe. As long as it doesn't erase itself, you'll be fine. You could copy it on a couple flash drives, whatever you want to do. For the sake of this video, I'm doing this on Debian. I'm going to install the Yubikey tools so I can add the intermediate private key directly to the Yubikey. And I'm going to put all of my files in the root's home directory /root. You could use some other folders. Those are the folders I used in the example. If you're following along, make sure you change all the domain names and stuff to match your setup. This is obviously my setup. So yeah, let's get into it. Oh, also a note, Yubikeys have pins, and you need to use the pin to access them. And the default pin is the kind of thing an idiot would use on their luggage, so you probably want to change it. Yubikey has a post on that. So OpenSSL, we're going to use OpenSSL to generate these certificates. The root private key, the root certificate, the intermediate private key, the intermediate certificate signed by the root key, and then we're going to put that key into the Yubikey. OpenSSL has a config file where we can put a whole bunch of options. I wrote a config file out. You can copy and paste it if you want, whatever. But yeah, let's copy and paste that. Most of it's not that special. Most of the big stuff is set on the command line anyway when we generate the keys, but just look through it and make sure it looks good to you. Over on my Debian system, we're going to make ourselves root with sudo su. Then we're going to move to the root home directory /root and make a new folder for our CA. Then we'll add this config file. After we generate the config file, you need to make sure all the directories are there for OpenSSL. And we also need to touch some files so they're created. It's going to make a file that has a list of all the certificates we've ever signed. If the file doesn't exist, it complains, things like that. Commands are on the blog post. Next up, we generate our private key using OpenSSL. And then we use that key to sign a certificate valid for 69 years for ourselves. This is the certificate we're going to import into all of our clients, so they all implicitly trust this private key. It's also going to ask us for a passphrase. This is used to encrypt the private key with AES 256. Type something good. Don't use 1, 2, 3, 4, 5. You know the drill. When asked for common name, this is the name that will show up on the certificate when you look at it in a web browser. So this should be the name of your root. So the ISRG root x1, that was Let's Encrypt's root. I'm going to call mine Tempest. And we're all done. This certificate that we just generated with the root private key, this we're going to have to copy onto all of our stuff all over the network. But the certificate authority we're going to set up later is going to host it on the web for us, so anyone can download it. That's going to make it a lot easier. For now, though, let's generate the intermediate key. The process for the intermediate is a little bit different. We generate the private key as we did before, but we can't sign it because the root key has to sign it. So instead, we generate a certificate signing request. This is where we attest to all of the things, the common name, all that kind of stuff, and sign it. Then we pass it upstream to the root and ask it to sign it for us. Then we have a complete certificate once the root has signed it. As part of this process, we're also going to need to generate a passphrase for the intermediate key, which we're going to need later. And we're also going to have to enter our passphrases for the intermediate key and the root key at the right times. And we're all done. Now that we have this intermediate key generated, we're going to import it into the Yubikey and then delete the private key. That way, the only way anyone can sign things with this private key is by using the Yubikey to do it. Can't forget to actually install the Yubikey tools first. Basically, this set of commands is going to install the Yubikey tools, start the service to communicate, and then it's going to write the intermediate file and the intermediate certificate onto the Yubikey in slot 9C. Now, the Yubikey has multiple slots. 9A, 9C, and 9D are the most common. However, there's about 20 other retired certificate slots that you can use for whatever you want. So if you use this key for other things, you could use one of those retired slots. I'm only using this key for this Yubikey. So I'm going to use 9C, which is the general certificate signing slot. But you're free to do you. It's again going to ask you for the passphrase for the intermediate private key. Make sure you enter that. It's also going to ask you for a Yubikey pin. Make sure it's not 1, 2, 3, 4, 5, 6. Enter that too. And we're all done. Let's check the status. YKman piv info. So this command shows us what's on the Yubikey in the piv application. We can see we have a 2048-bit RSA key. It's named the Tempest Testing Yubikey 1. Signed by Appleard's Adventures, blah, 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 blah. Seems good to me. So now that we have our Yubikey set, let's install the certificate authority. So I'm usually a big fan of virtualizing everything. In this case, though, I have real security hardware plugged in, and I don't want this to be able to move around a cluster because I don't want to have a bunch of Yubikeys plugged into every node. So I decided to use a real physical device running a physical operating system bare metal. I know that seems wild, right? But in reality, all the important stuff is stored in the Yubikey. So I could reinstall this no problem in an hour or two. This is a Dell Wise 3040 thin client. It's like 35 bucks on eBay. It's got like a dual core Atom, pretty awful. In either 8 or 16 gigs of eMMC, also pretty awful. Perfectly adequate for this. A Raspberry Pi would be fine too, but they cost more than this. So this is what I got. I installed Debian 11 Bullseye. As of the filming of this video, that is the latest version of Debian. I know I'm going to hear in the comments, but Bookworm, but Bookworm. Bookworm's probably like 3 days off as of when I'm going to release this video, so Bullseye it is. Also, there's a lot of things in these work instructions that are fairly specific to my setup, like the name of my server, the admin account named Appleard, things like that. So make sure you actually read through the instructions and change anything that's specific to your setup. I'll try to call it out in the video, but if you're having a problem, make sure you didn't use like my fingerprint or my name or something like that in your setup. Oh, don't forget to do your Debian upgrades too. Yeah, want to have updated packages before we continue. So the tool we're using is called Smallstep, and it has two binaries we need. Smallstep CA, that's the daemon, and Smallstep CLI, that's the interface. Now, the daemon needs to be compiled with support for Yubikey, and by default it's not, so we got to compile it ourselves. Thankfully, the CLI doesn't care, so we can download that from the internet. I have a deb package for the latest release version in the script here. Currently it's 0.24.2. So in the future, you might want to check what the latest release is on GitHub and get the deb package for that. They don't have a Debian repository, but their assets on GitHub include builds for a whole bunch of different Linux distributions, including a deb package for deb-based distros such as Debian. So we're going to go ahead and wget that deb file and install that deb file. So that will get us the CLI. That's the easy part. Next up, we need to install the tools we need to build the CA. It's written in Go, so we need a modern Go compiler. The latest version Debian has in backports is 19, and that's a perfectly adequate version, but we need to add the backports repository. So we got a command to do that. You update apt sources.list, add the backports repository, apt update, apt install Go, 1.19, whatever. So yeah, backports. We also need a few other tools, so Golang 1.19. We need Git, so we can download Git repositories. libpcslite dev. That is the library that lets us access smart cards. The Yubikey appears as a smart card. GCC, the compiler, make, the build tools, curl, all that good stuff. Then after we do that, we need to add Go to our path. When you add Go versions that are from not the Golang package, they don't add themselves to the path. So the Debian package Golang adds itself to the path. The newer versioned packages don't, so we have to say what version we want. After that, we clone the Git repository and we check out to a specific version. This ensures we're on release and not just the latest head from the tree. So I've called out version 0.24.2. Check what the latest is, check that out. And finally, we make install. And it sounds funny to make install, but make install depends on the binary, so we'll actually build the binary and then install it. How lovely. Then at the end of that, we tell Linux that this particular binary is allowed to bind to low-numbered ports. And yeah, that's basically the whole command listing. I don't think any of this is specific to my system, but read it first. I should note this will take a very long time. We're going to come back when it's done. Now that we got that build done, let's make sure it's installed. So we're going to run step version and then step CA version. So you'll notice there the release date for the one that I compiled is now in UTC, so not in local time. And the packaged one is different. So that's how you can tell that you just did the build, the release date matches the time you did the build at. So now we're going to set up a configuration file for our step certificate authority. And in order for it to generate this ourselves, we're going to call step init. And it's going to generate a whole bunch of keys for us. It's going to generate a root CA key. It's going to sign a certificate, generate an intermediate, sign that. And we don't really want to do that, but there's no way to tell it not to. So we're just going to delete those files and we're done. It's going to generate a whole PKI for us. We're going to delete all that, replace it with our Yubikey. But yeah, let's do that. So we need a place to put our CA. So I put it in etc step. We need a user for it. I named it step. And we need an environment variable called step path. So step knows where its stuff is. Then we have this command step CA init. This is where we give a name to our certificate authority. We give it a DNS name. This is how it knows how to find itself. Make sure this resolves properly. Mine is not going to resolve in your setup. I also have a line here to copy certs from the root CA folder I used earlier. If you keep your keys offline, you need the public keys, so the certificate file for the intermediate and the certificate file for root, you need to copy those in. So this should have generated a config file for Smallstep. It's a pretty big file. It should have generated it for us. We put our keys in. It should be happy with that. Since we're using a Yubikey though, we need to tell it to go find the Yubikey instead of using the private key file on disk. Let's do that now. So I put a little diff in my blog post. So we need to edit the ca.json file. And I put a little diff in showing what it needs to look like afterward. Obviously you use your Yubikey pin in the slot you used. I used 9C. Any of them should work. So we basically replace the key directive, which has a path to the intermediate private key, and we tell it that the key is on the Yubikey, and then the configuration for that. Make sure all your syntax is right. It will not like you if you type it wrong. See the diff on our website, make sure it looks right. Commas, squiggly brackets, all those goodies. So now we can test it. We're going to do that by telling sudo to run the step CA command as the user step. That should make sure it has permissions. And everything just works. So we end up with serving on HTTPS 443. That's a good sign. It bound to the port. It's happy. If your Yubikey is unplugged, you get an error saying like could not bind to smart card. It says error open Yubikey connecting to smart card. The specified reader is not currently available for use. Then you got to plug your Yubikey in. Just a note, if you unplug the Yubikey later, it won't crash. It'll just fail to issue certificates. So all of your Acme challenges will happen, and it'll be like, oh, oops, server error. And you'll be like, oh. Plug those Yubikeys in. Getting close to the end now. Now that we have a certificate authority and it works, we want to run it on boot. So we're going to use systemd. Systemd is all about running services on boot. I've got a systemd config file on the blog post. I'm just going to copy and paste that in. I don't think any configuration is necessary. And then of course when we're done, we daemon reload and enable now the service. So enable dash dash now, that enables it and starts it. Yay! So Smallstep can be configured with a whole bunch of provisioners, which are different ways of issuing certificates. By default, there is just JWT, and we're going to add Acme to that. Acme is the protocol used by Let's Encrypt. If we add that, then we can act as our own Let's Encrypt to our own services. So step CA provisioner add Acme. Acme is the name of the provisioner, so it's going to be funny. The path is going to be Acme/Acme, because it's an Acme type and it's the Acme name, but whatever. Just copy and paste the command. Oh, also, we need to restart when we're done. Restart step CA, not the whole system. Yay! Great success. Now we're all done. Now that we're all done setting up Smallstep, we can try using Caddy, see if we can get some certificates from this guy. So I spun up a Proxmox LXC container running Debian 11, the usual stuff. I installed Caddy from deb packages, and now we need to make that container trust our new certificate authority. So if you come over back to the blog post, I've got all the commands you need to execute. So our new certificate authority server publishes the root certificate file in a well-known location. So we can just wget that onto our local system. For this case, we have to not check the certificate though, because our system doesn't yet trust that root certificate. Once we download it, we can put it in our system's root store, then it will trust it from then on. So go over here to the container, paste it in. There we go, added one certificate. Now that it's been added, Caddy will trust it. Caddy has a directive to trust a root certificate other than its own for TLS purposes. But if the system trusts it in its root store, Caddy will also use that. So you don't have to add it separately to Caddy. Again, not a Caddy tutorial, but in the global section of the Caddy file, you can add an alternate location instead of Let's Encrypt, and that's what we're going to do here. I have a very basic example Caddy file on my website. Just going to paste that right in. Global section here just has the Acme certificate authority, and that's the endpoint. Remember how I said it was going to be Acme? So it's the URL of our certificate authority /Acme, which is the type of provisioner, /Acme, which is the name of our provisioner, /directory. So in my case, it's tempest.palette.net /Acme/Acme/directory. And then my test server also has a valid DNS record that points back to the server, so it can do the HTTP-L1 challenge, get a certificate, be happy, and it's always just going to reply hello world to everything. I didn't set up a website or anything for this. Let's copy that Caddy file. I'm going to start Caddy. So I could decide to do a TLS challenge instead of an HTTP challenge. Perfectly fine. Caddy did the challenge. Caddy got a certificate. Caddy's happy. So I took the time. I downloaded that roots.pem. I installed it on my Windows machine. I restarted Edge. Now we can see what it looks like in Edge. Proper TLS. It says hello world. But let's look at the certificate chain. So we have our end certificate for our site. It is trusted by the testing Yubikey 1, and that is in turn trusted by Tempest Root Lab. Since I installed Tempest Root Lab on this machine, and the certificate chain is valid, it implicitly trusts this website because I told it to trust Tempest Root, and Tempest Root was used to sign the Yubikey, which was then used to sign this web server via our favorite protocol, Acme, the same protocol Let's Encrypt uses. So now all of my websites inside my network can get TLS certificates that are trusted by my laptop, and I don't have to worry about these self-signed certificate errors all over the place. Nice and clean. Now the big reason I did this is because I'm on a path to do mutual TLS. That's where the client and server mutually authenticate each other. I'm not there yet, so this video is just authenticating the server to the client, but just like we authenticate the server and assume the server, or just like we verify that the server is valid, the server can also verify the same for the client. And that's going to come in a future video. So hopefully you enjoyed this tutorial. I know it was on the long side, but cryptography is hard. This is just an introduction. I do hope to set up mutual TLS where I can give certificates to all of my clients, have them authenticate to my servers. That we don't have to log into stuff. I can just log in by using a physical device or a Yubikey like this on the client side. Maybe a smaller one than this big one. But that's my goal long term. I got some other tiny Yubikeys I want to use on my laptop, my desktop, and things like that. That's my goal. So yeah, follow along, and don't forget to like and subscribe if you want to see more of this good stuff. You can check out my Discord link down below. I always love having people there. You can show off your own projects in the showcase section or chat with me about Acme Protocol or Smallstep or OpenSSL, whatever you want to talk about there. And yeah, as always, I'll see you guys on the next adventure.